My name is Ivo Kamrath, and I brought with me.
Hi, my name is Umang Gupta.
And we're solutions architect for Amazon Web Services. And today we want to talk to you about implementing distributed design patterns on AWS. And we want you to take away how you can apply the things that you have already learned in the past and applied in the past to technological shifts, like some of you may have noticed you might be going through at the moment. Now, we want you to remember that old school historical architectures are already found in your cities today. So you might find beautiful old buildings right next to skyscrapers where you come from, or perhaps even here in Berlin in some rare cases. And that's exactly the approach we want to take today. We want to show you a range of architectural design patterns and approaches that you can take that fit neatly into even a changing modern world of software design and systems design. Now, taking that into account, we want you to remember that the applications that we call legacy today were once modern systems, meaning that the problems and the solutions that architectural patterns have in the past been applied to have at that point been applied to very modern systems, which we now might look at and say, well, that's a legacy design. And if you take that thinking, those same solutions and architectural patterns and design methodologies will also apply to the current changing systems and technologies. Now, when you take an architectural design and when you design a system, it's very important to start simple. We don't want to add additional complexity just by adding a novel solution. We want to make sure that our solution eases the problem and provides a simple path through it, no matter how much complexity the problem actually brings. So today, we will take you through a couple of simple problems and show how existing architectural patterns are applied to them. Now, this type of approach that we want to take today is generally referred to as adaptive systems design. So to design my system to be cost-effective when adaptations are required. And adaptations to systems can become required when things like business requirements change, perhaps the company changes, maybe the system's purpose has found a completely new direction. And in those situations, you want to make sure that you can respond to those changes cost-effectively. But most commonly, system design changes are also adaptations of new technologies. So they are large shifts in technology. And that's something that can sometimes be frightening. So if you remember, some of you might, when you perhaps first had an internet connection and you went online and had no idea what to do there, or maybe your first mobile phone with nobody else to call, and now perhaps your first little prompt into a generative AI with no idea what to ask for. And that's exactly the situation where we want you to think back and say, wait a minute, I had these and these design patterns and these methodologies and these engineering approaches that took me through these problems in the past, and with slight adaptations will take me through these problems today. And we want to show you a couple of these, and we want you, for each of them, we will address a problem that is a problem adapted to the current situation of technological shift. And then we want to show a classically applied pattern and how that pattern can be applied to this perhaps slightly more modern problem. The patterns we've chosen today are not what we want you to take away. We want you to take away the approach of thinking about a pattern that you've applied in the past and how you can apply that to a shifting technological landscape. Now, the first pattern that we chose as an example comes from the domain-driven design, so the idea of taking business language into your design language. Now, this pattern addresses the idea of ubiquitous language. So if certain terminologies have different meanings, even though they're the same word, in different parts of your business domain. You can see immediately how that might fit into the world that we're now stepping into. So the pattern is called the bounded context pattern. So we want to start backwards from the problem and then kind of look at the pattern and try and see how this pattern, together with that problem, shows us how we can still adapt existing pattern to the world of perhaps generative AI. So the problem that we take you on today is going to be a little bit of a journey. We are a garden planning company. We want to provide modern gardening solutions. And being a software company, we also want to make sure that we don't need vast resources to do so. So imagine some of you may have tried source code completion, generative AI, and typed a couple of lines and then saw what the Gen AI suggested in the next couple of lines. But we want you to take that thought a little bit further. Imagine, instead of just suggesting a couple of lines, an entire team member is a generative AI. So you are assigning tasks to that generative AI, and these tasks will then be fulfilled and reviewed, first by the Gen AI and then by another team member. Now that you might now fear as certainly quite non-deterministic, but I'd argue most of our team members should be non-deterministic, in that they should surprise us with their solutions, right? Now, so that's the problem we're trying to solve. Now, you might already feel like, oh, that's quite a far-fetched problem, so let's see where we're taking this. Well, let's get back to what we are. We are a gardening company. So now, in the bounded context, we are defining two different contexts that may have overlapping terminologies and language of slightly different nature. So let's say we have one domain that designs a vegetable garden and another domain that designs a flower garden. Now, in a flower garden, a plant is a beautiful flower, and in a vegetable garden, a plant is an edible vegetable. And the same way, pots might be slightly different. They both call them plant, when in reality, they are slightly different objects. Naturally, they are plants, and to the people that work on them, they really are, but their actual functionality slightly differs. Now, that, on both sides, are our bounded contexts. They're bounded away. They don't actually interfere with one another. We separate them either through services in a distributed architecture or through system and software design in a localized system design. Now, for these two domains to communicate with one another, we define a shared context. And in this case, we chose the idea of using a shovel and water. So watering a plant is the same functionality for both parts of these slightly ubiquitous meanings of plants. They will still be watered in the same way. All right, so much so for what the bounded context pattern is. Now let's see with our problem in the generative AI space how the bounded context pattern can help us here. Now imagine your team member is a Gen AI. And that team member, we now asked to create yet another type of garden. So we wanted to design an entire domain, because we want to expand our gardening into a world of gardening that we had never even imagined before. Now, that team member, being a Gen AI, requires a context to interact with us. And that context is our shared context in the bounded context. Now, by defining that shared context with normally like an inter-service contract, we would have certain objects like data transfer objects that define that level of communication. We now have the same context defining the context and the context size that we give into the generative AI. Furthermore, we can use these bounded away objects to give the AI generation more flexibility without being afraid that it may accidentally overshadow some of the objects we have already created. So we can protect some of the implementation. Just like you would from another engineer that you don't trust, you can now protect some of your contextual objects from the generated content. Now, you might look at this and think, well, that seems really far-fetched. I don't have a Gen AI on my team that I can actually contribute with like that. But you could have. If you used Amazon Q and Amazon Code Catalyst, you could already, in preview today, assign an entire task in your source code repository to a generative AI and then review what the outcome of that is. Now, you would get a pull request, just like you would from any other contributor to your project, hopefully. And you could then see, all right, so that makes sense, that doesn't make sense, and maybe make some comments and changes and apply them to that. And you might be able to see now, okay, just like I would with any other engineer, I would make sure that my context planning and my domain language is clearly defined, and I can use it to protect it from perhaps the generated context and the generated domain that may be less clearly defined. And you can take this approach and further iterate over it to then have more and more tasks that better the contribution as well as your own addition to it. Now that's the simplest way how we show how a fairly clear domain-driven design pattern like bounded context can already be applied to the technological shift of generative AI. Now we want to take you through another two patterns. And the next pattern we want to go through, most of you will recognize as a type of behavior and perhaps not as a pattern, but let's have a look what that is. We want to go through the Saga orchestration. And most of you will already imagine, okay, so that's probably going to be some sort of retry logic. And yeah, you're absolutely right. So in a distributed system, it's not quite as easy to have to make sure that certain steps are consistent steps in one workflow. Now, as we said earlier, we might get contributions of content, and we might get a generative AI that provides content of our application, or maybe even parts of the application's production system, as we will see later in one of the examples. And that content may not be what we consider valid. We might outright say it's invalid. And for that case, we need to regenerate that content. Perhaps because of the non-determinism of the generative AI context, we might be able to just rerun it and get a better result. We clearly need some sort of validation. But we need to make sure that that validation and the rerunning and perhaps the generating of several parts is an atomic operation, so that the application doesn't keep going whilst we are still considering whether this is valid content. And that's where a Saga or a Saga orchestration comes into play. Now, the Saga orchestration normally requires an orchestration engine, so a centralized system that assures the distribution and the synchronization of the distributed workflow steps, and then makes sure that these workflow steps in a multi-step workflow are executed in the right order. Now, as opposed to an orchestration, there's also the idea of choreographies. That means that we don't have a centralized cluster, but we have several agents across the system that then apply the same logic of synchronizing a workflow in the same manner as the centralized orchestration would. Now, if we compare the two, a centralized orchestration system normally allows us to more easily deploy the cluster for orchestration. It also allows us to concentrate our development of the orchestration system to just that part of the infrastructure, whereas a choreography might seem more novel to us because it's just running alongside our system and scales with it. But yet, in comparison, the two really come with the one major disadvantage that we're adding significant infrastructure when we have a centralized orchestration system, and we want to show you why that's not a problem on AWS. Now, let's go back to our actual application of this pattern. So we have some sort of deterministic written code, something that we wrote, several steps that have to work in that order, and then we have a more non-deterministic generated part of the system. Now, that generated part will then require a type of content validation, as we said earlier. And that content validation will then either validate that the path that was non-deterministic actually did what we wanted it to do, so we generated something that makes sense, or it might say, nah, that doesn't make sense. Now, content validation is a very easy word, whereas when it comes to generative AI, it's a very complex task. But it doesn't have to be if we apply the common logic that we use when we have these Saga patterns. Now, let's have a look at our example of gardening. Let's say we have an input choice of plants that we want to plant. So we say, I'm going to plant some roses, some strawberries, and some blueberries. I'm going to need different soil. So I also have some telemetry system, some IoT system in my soil that gives me information about the actual soil. You might have seen one of the stands today that it did exactly that. And then, based on these two inputs that I got from different parts, but in a deterministic manner. So I quoted that, right? So that's really something I know how the output will likely develop. And then based on that, I hand that over to my generative AI system and prompt for a garden plan. Now, a simple validation of that could be simply to check whether the garden plan actually contains the plants that we wanted to plant. That's a good step, right? That would be a valid plan if at least it holds the plants. And furthermore, we can also validate whether it mentions something around the soil. So that would be a very simplified validation of this. And then based on that, I go ahead and visualize that plan or take it further. Now this graph, and keep it in mind, keep it in your mental eye, that's exactly how it's going to look on AWS. So if you use AWS step functions, and here we provided a small example state machine, slightly simplified, you can use that model-based design to have your centralized orchestration engine, but you do not have the actual issues of a centralized orchestration cluster because Step Functions is a serverless service, meaning that you do not need to manage the scaling of the actual orchestration system. Now, Step Functions integrates with AWS Service natively. So if you want to read something from S3, let's say we had a web interface that neatly wrote our choices of plants into S3. And we now read that out again in our little state machine. And then we create a couple of jobs in the IoT world that get and gather and aggregate some telemetry. And then we'll take that gathered data into AWS Bedrock. And again, it's a native integration with AWS Bedrock that you can use today, that you can then immediately from AWS Step Functions trigger and move on. Now the result of that, because this is a state machine, it will accumulate more and more state in its return. The result of that, we can then hand into a validation lambda, which just quickly checks, are the roses in there? Are the tulips in there? Is the soil actually mentioned in the plan? Some simple checks, or maybe even more complexity. And then, based on that evaluation, we'll find out whether the plan is something that we liked or not, and then we might be able to go into an optimization step. Now, this optimization could be just like you would on a localized LangChain. Perhaps you look up, maybe the plants were in Latin, but the models more generally apply to common names. So you'll just translate the Latin names for the common names. Or you might go ahead and say, well, some of these I'll just reorder. So whatever validation and regeneration would lead to a better example. And then we go back and regenerate again, and then you have your retry logic and your simple little saga. Now this saga could also be used to have several prompts, and then have results of prompts serve into other prompts, so you can have some sort of distributed LangChain. And you can see how the added complexity of a localized system could already heavily increase here by having more infrastructure in a distributed manner. All right, and then here on the other side, we showed you PartyRock.aws or Amazon Q applications or apps, which allow you to quickly, rapidly prototype the application that you want to try. So you just go ahead and with a single prompt create exactly what you see here. So we just prompted it to please give us a garden planning app that takes these two types of inputs, and then we'll see what else happens. This type of rapid prototyping from 1995, again, a software methodology that we're all well aware of, can easily be applied to this generative AI approach of prototyping, meaning that I make a prompt, and based on that prompt, I see whether the result is actually fitting to the current level of models. What might it look like? It might come up with additional ideas like, why wouldn't you have a garden planning assistant that is aware of your garden plan? So we hadn't even thought about that when we initially prompted it to give us a garden planning app. Now you can see how these two patterns are simple solutions to perhaps more complex problems that you've already been aware of in the past when it came to software design problems. And with that, I'll hand over to Uma.
Thanks, Ivo. So, yeah, before I start talking about the following two patterns, I want you to start with what Ivo just ended with, simple patterns to solving a little bit complex solutions. If you remember, one of the initial slides talk about starting simple and only adding complexity when it's called for. So what's a simple application? What's a simple use case, an application? Let's imagine there is a traditional system where you have a single data store. An application is reading and writing directly to the data store. It could be a database, object storage, file system, whatever. I don't know about you, but there has been so many cases in my experience where I had wished if only I could travel back in time 5 years back and talk some sense into the developer who made the choice going with that database. Like, why did you go with that database, which now currently doesn't work for what I have the problem to solve with? So starting with simple bounded context, we generated some garden plans. Then we added some more logic, some try-catch with Saga orchestration, and we validated that the garden plans are ready to be deployed. Now, what could be a problem that you would run into, or you may already be running into? It's the data sets or you're working with may not be suitable for generative AI. You may want to have to export it to some different format. You want to interchange the formats into some other type of storage. or you may have a different scaling requirements because you have different applications. You may have a chatbot, you have a search that have like different requirements to what kind of data they work well with. And you may find yourself into a situation where the data store you have right now may not work with. How do we solve that problem? Or how do we create a system that allows us to make changes or allow us the adaptability to make the design future-proof? With that, I want to start talking about event sourcing, not just because at AWS we love talking about event-driven architectures, but that's the first part we used, the first pattern in a 2-pattern series, which actually eventually will help us to the solution. So event sourcing is a pattern where we append the state-changing events to a data store. And the idea is to generate the current state of the object or any point in time back in past state of the object at runtime when you need it. So in a traditional CRUD-based system, so create, read, update, and delete system, you would be directly writing, whenever there is a write operation coming in, you would be writing directly to the data store and reading it directly from it. Here, the idea is not to store directly to the data store, but some kind of a storage we call event store. And there, you will have the event stored, which have some business logic that would make the state of the object change. But now you'll ask, how does it help me? Let's take a look further into where this type of system, like event sourcing pattern, works well. So event sourcing works well already with workloads where you don't require real-time data processing. So you have an event store, but you don't have a final object that you want to work with, that the application wants to read. So whenever you want to read the object in event sourcing, you would have to like derive the current state and then use it in your application, which kind of doesn't scale. And we are talking about distributed design patterns which allow us to scale. But anyhow, event sourcing still is very beneficial where in some applications where you want to have some kind of like audit or tracing, or you don't want to, you want to replay past events. But again, doesn't help as it is in our use case. And that's where enters command query responsibility segregation. So the idea is, as the name suggests, we want to segregate the responsibility of commands, which are the write operations, versus the queries, which are the read operations. So you take the write operations, like writing it into a database. So the events that have side effects, that change the model, and separate the logic which does the writing part and totally decouple it from the reading part. This not only allows you to scale both reads and writes separately. So for example, in a read-heavy system, in case you have in future some requirements that might have tied its performance to writes, you would decouple it from the write operation and the read operation so that you can scale those two individually. And this works on top of event sourcing. And here's a visual representation that can help you understand a little bit better. So on top, you see all the commands coming in. So the commands would be all the write operations. And instead of writing directly it into a data store, what we are doing here, or what the idea is, to convert those into events, the same events we talked about in event sourcing, and store it into event store. And now, for the reads, for the queries, we generate the models you want to use for your different applications based on the event store model, and then create your own data store or multiple data stores, and then your applications read directly from them. So you now have you now kind of have two different applications. One is responsible for commands or writing it into some form of data store, and then one application which is responsible for allowing all the query operations. Again, you might be thinking, what does it all mean, or why are we talking about it? So imagine the same thing. Like you would say that this is basically the same thing you are doing in crude application. We talked about the system, and I can do the same thing. How does it help or in my distributed design system? So going back to our initial problems, we now have generated the garden plan. We have validated it. But now how can I use it, or how can I store these garden plans so that my application is adaptable and flexible and also scalable to my requirements, not for today, but maybe also for 5 years on down the line. So in here, imagine that I have generated those garden plans, or we have generated those garden plans, and now we are feeding it into an event store. And from that event store, I am now generating my data, or like my model that I want to work with, and then using that data in different forms to query the application. So for example, in this case, I'm providing tulip, strawberry, and rose gardening schedules. And then I have built a chatbot which allows me to query those models directly. For example, what are the May tulip actions for me? What do I need to do in May for my tulips to grow? And here, you can see that I am storing the data in one kind of like chatbot, but you may also want to build a search engine or some search application, and you may not even care about plants, vegetables, for example. You only want to deal with flowers. So what do you do then? Then you apply the bounded context and go back. Only generate a model based on the events that are concerning the plants. So you can transform or create a separate model only focusing on plants. So you're also reducing the size of data sets whenever you're working with, depending on what kind of application or what kind of use case you have. And it also gives you the flexibility. Let's say I created a model, and now I'm storing it into an S3 bucket for this example. But now you want to work on a more complex application where you may need a vector database, or maybe you want to extend it and store some form of relational database and have the data represented in some different form. And that kind of gives you the flexibility, and you can see how it looks like, or how does it actually work. So on top, you see the commands I'm using to create this application. It kind of adds on to what Ivo mentioned during the Saga orchestration, which now, for the simplicity, doesn't have step functions. But basically, we are generating the garden plans using Bedrock and then storing it into Amazon Managed Streaming for Apache Kafka, MSK. And then that's my event store here. But you have the flexibility. You can have DynamoDB or Kinesis, whatever you are comfortable with or what the application requires. And that would be the event store where I will be then generating my other data stores from. So in this example, I have an AWS Lambda, which is then reading it from the event store and generating some objects on S3 and storing it on S3 bucket. And then I have an Amazon Q business application that's integrated to the S3 and then answering some questions. But imagine now I want to build another application, a search application, as I mentioned earlier. What I need to do is not change anything that's going on the top side about the commands, but only I need to add another Lambda function that then writes the events, or like performs the event stored into an object and stored into some kind of vector store or whatever application you want to build with. And then have that application created, the search application read, instead of the Amazon S3 bucket, read it from the data store that you created. You can replace your Amazon S3, so it kind of goes back to, like, if only you could go back in time and change the data set you were working with. So you would be able to replace your Amazon S3 bucket with some kind of other data store that you want to work with, or you can also extend it and have two data sets or data stores at the same time. Maybe for comparison, maybe for different application reasons, and it kind of gives you the flexibility to do those modifications when you want them, and you don't have to think about what's the perfect database that's going to solve your problem today and also in future. With that, as Ivo initially mentioned, the key takeaway here is not about what these 3 or 4 design patterns are about, or how do you apply these specific design patterns to your application. Instead, the idea is you can apply these distributed design patterns, or more, the other ones that are out there for so long, that have been well tested, to design and build your modern applications, generative AI applications. Those still apply to the modern problems. And when you are looking to modernize your application, you want to make them future-proof. You want to reduce the cost it would take to make the changes in future. And that's why you build those domains adaptively to suit your generative AI use cases. Talking about different design patterns, here's a link that you can use already, which talks about the 3 design patterns we talked about, and it also has more design patterns that you can look into. It's on AWS Perspective Guidance. It talks about cloud design pattern architectures and implementations. And with that, this is the last slide, keeping you from here between you and the happy hours. And with that, thank you for joining our talk, and thank you for attending AWS Summit Berlin.
Thank you.